In this video, we will talk about the role of a Zener diode on the load resistor connected in parallel with it. We know that Zener diode is mostly used for protection purpose. So using numerical problem, we will find out how does it protect load from getting damaged or getting short circuit. So firstly, we should recall this concept of forward bias, no bias, and reverse bias conditions for diode. Then we have this type Zener diode, which operates actually in reverse bias condition. And then we have this threshold voltage, which is called VZ or Zener voltage. So once this threshold voltage is reached, the diode starts conducting the current through it. So what we are going to do is firstly, we are going to assume that this diode does not exist in the circuit. This does not exist, and we have a series circuit. So we will see how this voltage at the load operates in that condition, and then we will add Zener diode in the circuit and see how it affects and limits the voltage. So firstly, we will calculate the load voltage. So the formula for that is written over here. We will derive it, don't worry. But if you are good at electric circuits, you will already know that when resistors or any components that are connected in series, its voltage can be directly calculated using this formula. For example, if we want to calculate voltage for this load, so this can be calculated directly using this resistor RL divided by the total resistance in this circuit. So the total resistance in this circuit is R plus RL, right? And then we have to multiply it with the input source voltage. For example, this is just an example. If you want to find voltage across this VR, right? So that will be VR is equal to resistance, right? That resistance is R divided by total resistance. So total resistance is R plus RL. Okay. And then this whole multiplied with the input source voltage. If we had another resistor over here as well, then the total resistance, let's say this was R3, then total resistance would become R plus RL plus R3, R plus RL plus R3, and similarly we can also derive the voltage across this. This is actually called voltage divider rule. Voltage divider rule. Okay, you may be familiar with this, but don't worry, in the next slide we will derive this equation. So let's derive it. So in the first case, we want to see how load voltage performs when there is no Zener diode in the circuit, right? So first step is really easy. We apply Kirchhoff's voltage law. So this becomes minus E plus VR to this component and then plus VL equal to 0. We have written that over here. Now we know that the formula of voltage is V is equal to IR. So we can use this equation to our advantage and replace VR and VL with this equation, right? So VR will become IR times R, right? This is the current through this, let's say that is IR, and this is the resistance. So IR times R. VL will become, let's say the current through this is IL. So IL multiply by RL. So this becomes IL RL. Now we know that for this case, there is no Zener diode here. So this will be actually a series circuit. So what happens in series circuit is that the current throughout the circuit will be same. So IR will be equal to IL. So I will simply replace this IR with IL using this logic and then derive this equation. So let's do that. Minus E plus IL R plus IL RL equal to 0. And then I will take IL common from this and move everything on the other side. So IL times R plus RL is equal to E, right? And IL is equal to E divided by R plus RL. Now, this is the current in the load. To find the voltage, we know this formula. VL is equal to IL RL. So I simply have to multiply this equation with RL and I will obtain this equation, which we discussed in the previous slide as well. Now we will plot this graph between VL and RL. What happens when the load increases? So how will VL operate in that condition? So let's go to the next slide. So in this slide, you can see that we calculated this load voltage, right? For the case when there is no Zener diode operating in the circuit. Why it is not operating? Because we are assuming the voltage drop has not reached the Zener voltage. Okay, if you recall this graph, which we saw in the first slide, it was something like this. This is actually VZ is equal to 10 volts. So we have this region where this will be acting as an open circuit. So now to plot the graph between RL and VL, we know that E is constant. It is constant for this numerical problem as 20 volts. R is constant, RL is also constant. So when RL is 0, we will know that VL will be 0. So we will have this point over here, right? Let's say RL is 1. So if RL is 1, we will have RL again 1. And this R is also, let's assume it as 1 kilo ohm. Okay, by 1 I mean 1 kilo ohm. Okay, so this will be 1. So the net result will be 0.5 E, right? 1 divided by 2, this will be 0.5 E. So this will become some value. So that is over here, right? 10. So the point is when RL increases to 2, so this will be 2 plus 1. So this becomes 2 by 3, which is equal to 0.66 E. So take notes of this. When RL increases, this value is increasing, right? This will be somewhere over here, right? So when RL increases, VL also increases, but it will reach a threshold value of almost 20. It will not reach exactly 20, but it will reach almost 20. Why is that? Because let's assume RL is 1000, right? Then it will become 1000 plus 1. So this will be somewhere like 0.99 or something like that. And then it will be multiplied with E. E is 20. So this will be almost 20. So we can see our graph will increase like this and it will reach the applied voltage. It will reach somewhere the infinite time, the applied voltage of 20 volts, but it will never cross this 20 volts. Okay. Now, what happens when this threshold voltage of diode is crossed? Vz is 10 volts. So that is our graph over here, right? What will happen in that situation is we will discuss in the next slide. In this slide, you can see when Zener voltage is reached, which is 10 volts, our graph will be linear and load voltage will not cross this 10 volts. So load voltage maximum will be Zener voltage. Minimum it can be some value over here. Why is that? The reason is Zener voltage or Zener diode. Let's talk about diode. Let's talk about this diode. So this diode, let's say Zener, this is in parallel with this load, right? RL, they are in parallel. So when two components are in parallel, their voltage will always be same. So we know that this node is actually a common node between Zener diode and our load, right? So this will make these two components operate in parallel. So once 10 volt is reached, before 10 volts, this will be open circuit. But once 10 volt is reached, current will start flowing through this. Once current starts flowing through this, the load voltage will always be equal to the Zener voltage. So we can see that the graph will be 10 volt once Zener diode starts operating. Okay. Once again, just to explain it to you, Zener diode over here and this load voltage. Let's write it over here. Zener diode and load, they will be in parallel with each other. Parallel with each other. So once they are parallel with each other, what happens is that the Zener voltage will be equal to load voltage. No matter how much input source do we apply to it, this will never cross that because they are in parallel. And we know that in parallel, voltage will always be same. So for the initial region, when the diode, which is Zener diode, will not be operating, we will have some curve. But once Zener region is reached, we will have this 10 volt as a threshold voltage, and load voltage will never cross this 10 volts. So this is the reason. This is the reason that Zener diode is actually limiting the load voltage. Okay, because this is Vz is equal to 10 volts, and V load will always be at maximum of 10 volts. So this is how we can protect our load from getting damaged. For example, we have a threshold voltage of 10 volts for some component. So we can attach or bring the Zener diode in parallel with it with the 10 volts value. And due to this 10 volts value of the Zener diode, the load voltage will never cross that value and it will be protected. So this was the theory about what happens when a Zener diode starts operating. In the previous slides, we saw when it doesn't operate, we will have a graph like this. It will reach some value, and that value actually depends on the input source. But once we introduce Zener diode, then the output load voltage is limited, which acts as a protection for that load. Now we will do some mathematics and try to derive the currents. So we have this IR current here, right? And it splits because we have this node. So we will have IZ over here and IL over here. The reason we want to find this current is that we want to see how much power does this Zener diode consumes. So let's go into the next slide. So firstly, what we are going to do is that we are going to find the voltage value in this resistor. Previously, when this Zener diode was not operating, we knew that using voltage divider law, VR will be equal to the resistance of this component divided by total resistance times E. So if we know the values of resistors, we can find this directly over here. But now, when Zener region is reached, then this will change. So we will apply a Kirchhoff's voltage law in this first loop. So which is minus E due to this one, plus VR due to this component, and then plus VC. Okay. So minus E plus VR plus VC equal to 0. E, we know that it is 20. VR, this is what we want to calculate, and VZ is 10. Now take notes of this key point over here. We have plus VZ. If you look at the diode, this is plus terminal and this is negative terminal. But that's the key concept of Zener diodes, that it operates in reverse bias. So once the current starts to flow through it, this polarity becomes plus and this becomes negative. Okay, so that's why we are writing plus over here. So using this formula, we will calculate VR equal to 10 volts, right? We calculate that, and it's obvious to us when this is minus 20 and this is 10. So we are only left with 10 volts over here because according to Kirchhoff's voltage law, summation of all voltages should be equal to 0. So minus 20 and this is 10. So this is obviously 10 volts. Now we can calculate the current through it because we know that VR is equal to IR times R. So we can calculate IR, right? Next step is to find, okay, let's find this IR value firstly. So IR is equal to VR by R. So VR is calculated as 10 and resistance is 1 kilo ohm. So this becomes 0.01 ampere. This is IR, right? Now I want to find this Zener current, right? So using KCL, which is Kirchhoff's current law. So any current entering to the node, which is this node, is equal to the current leaving that node. So we have this IR is equal to IZ plus IL. But firstly, I should find the value of IL. So we can do that using this formula. Once again, IL is equal to VL by RL. So since these two components are in parallel with each other, so its voltage will be same. So IL is equal to 10 divided by RL. So let's assume RL is 2 kilo ohm. Let's assume that. So we will get IL is equal to 0.005 ampere, right? Because this is kilo, so when it moves upwards, we will have milliampere. So this will become 5 milliampere. By the way, I just realized that this is correct. This is 10. So this is correct. I thought this is 1 divided by 1 kilo. So we got this value of IL. I also have value of IR. So how I am going to calculate the value of IZ? It is really simple. Using the Kirchhoff's current law. We discussed this earlier, that any current entering to the node is equal to the current leaving that node, right? So IZ becomes IR minus IL, right? So we can see this over here, and then we can calculate IZ as 0.005 ampere. So once we calculate this current, now what I can do is that I can calculate the power dissipated in this diode. So P is equal to VI, which is also is equal to I square R. And then there is also another formula, V by, if we replace this I by V by R, so this is also equal to V square by R. We have all these three formulas for calculating the power, but this one is much easy because we have the value of VL, we have the value of IL. So we can calculate the power dissipated in Zener diode as 50 milliwatts. This is very small power, right? So what we saw in this example is that the role of Zener diode is that it limits the output voltage. We discussed that in this video, that to discuss this output load voltage, we can introduce a Zener diode. So this load voltage will never cross the Zener diode voltage, which is 10 volt in this case. If this was 12 volt, then the maximum voltage across this load will be 12 volt, right? So if this was 5 volts, this maximum voltage across load will be 5 volts. So the advantage of using a diode, which is Zener diode in this circuit, is that it will limit the output voltage. So if we can limit the output voltage, it means that we can protect our device or circuit according to our needs. So this was about Zener diodes.